Three speakers today. Grant Hagan is the guy that you saw. He's actually in Dallas. He is one of Beck Construction's virtual design coordinators, virtual design managers. And then we've got Alejandro I did pronounce his name 5 minutes ago, but short-term memory, I'm not going to try it. So Alejandro is here in person. He is one of their local virtual design coordinators, consultants, managers, dudes. And we also have Steve Blumenbaum, who is with Walter P. Moore. He is on the technical side for the structural engineering team. He's going to be popping in and out. There'll be a lot of different jumping in and jumping out. Also, we've got Brian Wilson, who is online. He just got back from a trip to Paris, France. That's going to change the landscape of the Tampa Bay area. So it'll be kind of cool. So with that, again, here we go. So we've got the opportunities for those of you that are online. We do have the opportunities to engage in this project a bunch of different ways. Today we're going to be talking primarily about the Honors College team, but this is really a generic presentation that could be affecting any project. To get more about the different projects, go to Bulls Connect, go to the AEC Experience, and then right before Thanksgiving, we're going to do another site visit. So that ought to be exciting because by then we hopefully should be starting to erect steel. We're pretty much done with concrete. We're going to be close to erecting steel, both on the Honors College and the Wellness Building. So again, changing the landscape for USF here. So with that, I'm going to turn it over to our friends from Beck. I introduced our speakers already, so we are moving over. And I'm going to go mute my mic. Am I muted? Thank you.
Can you guys hear me okay?
Yep.
Oh. All right. My name is Grant Hagan. Like Steve had mentioned, I work here at the Beck Group out of our Dallas-Fort Worth office, which is our main office for our company, but have a really unique opportunity to work with a lot of our regional offices, which in the Tampa area, this project falls under. So excited to be here with you guys today and excited to go over a lot of this content. So the first kind of thing we're going to go over, I guess, Alejandro, do you want to introduce yourself next, and then I'll get into my content?
Go ahead, Grant.
Okay, perfect. So the first kind of way we wanted to kick this off was really just giving you guys a high-level intro of what the virtual world of our industry is, of design and construction. There is a lot of acronyms, and it's a very acronym-heavy part of our industry, but we really just wanted to kind of focus on two of them that's really related to this topic specifically. So to kind of kick that off to start, we wanted to ask a poll question here, which you can see on the screen. Really, one of these acronyms we're going to be talking about is BIM, or BIM. I'd be curious to know from the poll, and I apologize for the typo that you probably see in point 3, but just curious if anyone really knows what this acronym is, what it stands for, and we are going to put that out there in the poll. So go ahead and feel free to submit that if you're with us online, or think about your answer there if you're in the room. So I see some of those responses coming in, so that's good. We're going to transition here to really kind of how, so I guess to spoiler alert here, I see a couple more responses coming in. So for those that haven't submitted yet, you're going to get a little teaser here, but it does stand for Building Information Modeling. So what that means is really in the context of these kind of two parts of the industry that we're going to focus on here today, which is in the design phase and the construction phase. There's kind of a roadmap and a life cycle of these jobs that you guys are going to see and interact with on your campus. But to kind of give a high level overview of that, this is really just a graphic that we like to kind of help explain how building information modeling really impacts both the design and the construction phase. So whether you're really in the beginning stages of a project with programming to conceptual design all the way out to detailed design that you can see there on the right hand side, and then transitioning over into the construction phase, where you're starting to build, obviously from that model. That's really where we start to get into some of these items as it relates to actually physically building that out in the field. So we really just kind of like to show this as a roadmap of really building information modeling is this concept that really runs deep through design all the way into construction, which is going to bring up our next topic here, which is another acronym of VDC. And so these two acronyms are really important to kind of understand when you want to talk about this virtual world of design and construction. Really, my hope in the next couple minutes is really just to give you a really good understanding of these two terms, what they mean, why we need to know them, and how really they are making an impact on our industry for you to have a little bit better insight into these projects that are going on y'all's campus. So the first one being BIM, we already obviously talked about it a little bit, which stands for Building Information Modeling. The key to this as a kind of a definition is really this idea is it is a noun. It's a thing or a tool, or in some cases, consider it like a hammer, right? Think of it as something that's like actually like physical. So this definition here, really the key words that we wanted to highlight was a digital representation or information. When you think about BIM or Building Information Modeling, it is really a noun or a thing or a tool. And the really important thing to that is there's a lot of tools that our teams use to create these buildings virtually. One of which that we're going to transition to is a tool called Revit. So Revit is a platform that our design team and construction team, and really a lot of the consultants that are adding information to these buildings, is producing in a virtual world. So everything from the glass components to the steel components to the stairs, which you can see here, everything is being modeled virtually. And this would be considered a BIM tool, a building information modeling tool. And the important part to that is to understand that it is just a thing. You don't just throw Revit or modeling in a project and expect it to change or expect it to have any increased value. It is a part to that process. And so another tool that we would use, so if Revit was more on the design side, on the construction side, another BIM tool that we would use would be a laser scanner, which is what you could see here. Typically, this is kind of known as a surveying piece of equipment, but it's something that our construction staff uses to really understand the built space that we are either continuing to build on or start to build from. And so I think this is a video here that Alejandra, if you click on it, it'll start to kind of move around and show you that our ability to recreate this space. A lot of people have kind of called it either a digital twin or a digital representation. I know you're kind of getting a little fuzz here, probably on the Teams chat or in the room there, but really what this is it's a digital reconstruction of the space, and that is done with a tool, a building information modeling tool, as a laser scanner. And so what I wanted to show you was more of the architecture side of it in what Revit is as a BIM tool. And then on the construction side, which would be a laser scanner, which you're seeing here. This is kind of a preface to a couple of things we're going to talk about later in the presentation, but wanted to give you an example of, again, building information modeling. It's a thing, it's a noun, it's a tool. Architecture-wise, Revit. Construction-wise, a laser scanner in this example to give you kind of that realm. So the other acronym that we wanted to talk about was, what does VDC mean? What is that kind of, how does that play into it? So VDC stands for Virtual Design and Construction. And so the key words that we highlighted here was management or work processes. Think of this as more of a verb or an action or a process. So from this standpoint, really what we're doing is we're taking those tools and we're starting to put them into different processes that help both our architecture team and our construction team. So a list here that we wanted to show is really some examples of what does that mean, or what are some VDC processes on the architecture side and on the construction side. So what you're going to see here on this next slide is just some examples of what some of those, here actually, what this example here that I was trying to show was, okay, so you take a hammer and a nail and some framing, right? And you're putting those tools together into a process. And so overall, if you kind of keep clicking through those, you'll see that is the action of framing, right? So you're taking tools or materials and you're putting that into a process, and we're going to call that framing. That's kind of the analogy if we're sticking with kind of this hammer and nail and kind of smaller analogies of what this looks like, right? So as we get to some of those actual or tangible examples here on the next slide, what we really wanted to show you was this idea of what does this actually mean? Like, what are some VDC examples or processes on the architecture side and then on the construction side as well? And so really a lot of these processes are built from tools that we're using to help us do different studies or different things that we may not necessarily be able to do with traditional methods or procedures, right? So on the design side, that may be engineering analysis or different environmental analysis that we're doing, maybe some renderings or visualizing things to help put people in those environments, some lighting analysis of how do we want to position these buildings on the site based on different lighting factors from sun and shading and all that, to on the construction side, actually building these buildings out on the site, right? So whether that's like site logistics or layout or virtual mock-ups to see what these things are going to look like. Again, we're taking all of these tools in the BIM world and applying them into processes into the virtual design and construction world. And so that's really what we wanted to kind of give you guys, is really a baseline of understanding of, okay, there's a lot of acronyms in the construction and architecture industry, but two of them that are really important and are applicable to here is this idea of BIM, or building information modeling, and VDC, which is virtual design and construction. So what I'm going to transition to is Alejandro, and he's gonna talk a little bit more about what does that mean and how do we kind of take some of these VDC processes into action in the realm of considering what that looks like for design and construction.
Thank you, Grant. Okay, does the mic work? Yep, we're good. Perfect. Well, good afternoon, everybody. Again, my name is Alejandro Iturriaga. Thanks for your time, and I appreciate your attention and your time, because we took a little longer than expected for technology. So thanks again. So BIM considerations for design. First poll question that I have here for you guys is, if this works. Probably not. Try it over here. What do you consider when you select where to live? So I don't know if this is the first year of you living here in Tampa, but what did you consider when you moved to Tampa, or when you moved to a new place to live? Do you consider who will live with you, and do they like to wash dishes? Maybe. Do you consider renting 2 apartments and using one for parties? What about, does the apartment have hyper-fast internet because you want to watch movies on Netflix and you want to stream video games? Or do you just say, I should just have my apartment or my house designed by an architect? What do you normally do? BIM Execution Plan is something that we do to start out a project, to plan a project. So just the way you guys are planning out where to live, we have a BIM Execution Plan that talks about who you're going to live with, right? Who are the team players? Do they know what you need for them to know in order to be part of your team? Do they have the capabilities? Do we have the software? Do we have the hardware? Do we have all the technology needs in order to do this project? In a way, that's what you think when you're looking for a place where to live. The USF has their own BIM guidelines and standards. A lot of other companies and institutions have this. So if you work for a hospital, let's say the VA hospital, or if you work for the U.S. Army Corps of Engineers, they will have a BIM guideline. They will have a standard of how they want the projects to be. So again, we're going back to the apartment you're going to live in. What do you normally do? You see this 2D floor plan, right? It tells you where things are at, where the bedrooms are at, the restrooms, bathrooms, the kitchen. And nowadays, a few companies provide you a 3D and isometric view of that, right? That's pretty common. So that's what you do when you go and you look for a house on Zillow, probably. This is a floor plan of the Honors College 2D drawing. It's just flat. It's just lines. It's showing us that level, this specific, it's the level 2. This is a zoomed in version of that, level 2. So we have the restrooms, corridors, some elevators and stairs. It's showing us in 2D drawings the location of that. Well, we can also do that in a 3D model, and from the 3D model, we can actually export it. So the information from the model can be exported. So this is just a little video of that model where we extracted the 2D drawings from. This is at Honors College that at some point you'll be working in there, having a coffee, going to the restroom, walking up and down the stairs. So there are design drawings, just as we mentioned, and there are fabrication drawings. What's the difference between both of them? Anybody know? No? I think you. Okay, so it's more of a detailed version of a drawing. Perfect. So most of you maybe have bought furniture at IKEA, and you know how those manuals come, right? 42 steps to build that. What is that? I think that's like a desk, a gaming desk, right? 42 steps for you to have a gaming desk. So remember we talked about knowing your team, and if that team knows how to wash dishes, if that person knows how to wash dishes, well, this might come in handy. You might need to work with and live with someone, right? So they can help you put that furniture together. So that is right. Thank you for that. BIM has dimensions. Today we're only going to talk about 2D and 3D dimensions, but it also has more dimensions. 2D, we talked about the drawings, just floor plans. 3D is that geometry, right? The 4D is like an animation of that. So when you're playing video games or you're watching those animated movies, it's an animation of the project, of a building, of how it's going to be constructed, and it's tied to time. Number 5, it's cost. So just like if you go to an Amazon store and you can buy certain things, you have a cost tied to that information or to that object, to that 3D object. 6D could be sustainability. So nowadays everybody has an Amazon at home and you have smart devices and you can turn off and turn on. Sustainability could give you information about the source of that material, of where it's coming from. It could be used for LEED, right? LEED certification. And 7D, a lot of people in the industry say it's only 60. There's no 70, but it's actually evolving. Now we have 70, we have 8D, we have more. But facility management is now you have a building that you can have information for your facility management tools. So probably you guys have playing Minecraft, right? That's just a 3D representation of a house, but it's not really detailed. We don't have 4D, 5D, 6D, or 7D in that. It's just a geometry, right? And it's just generic boxes. So that's important for us when we're modeling. We want to define what we're going to model. Can we have a box representing that house? Or can we have the actual perfect geometry of that figure? So let's talk about a kiwi. Everybody knows a kiwi. The LOD would be the level of development. So how do I want that kiwi to be modeled? Can it be represented by a cylinder, by a kiwi, or by a box? How do I want that to be detailed? And then the information, right? When you go to the superstore, Publix, or any superstore, you look at the kiwis and you know where they're sourced from, right? They could be from New Zealand. You can know the price, but that's all the information you know. You don't know the color, you don't know the price, you don't know, oh, well, the price, yes, I'm sorry, the smell, and the expiration date. So you might want to have more information in your 3D model, in your BIM model, your information model. That's part of the LOD. I'm going to hand it out to Stephen. Thank you.
All right, good with the microphone, Steve? All right, great, thanks. Hey everybody, Steve Blumenbaum. I'm the Director of Construction Engineering for Walter P. Moore, and we were the structural engineer on the USF Honors College. So this slide is kind of interesting. Out of curiosity, how many of you are in the architectural engineering, building construction industry major? Okay, a few of you. That's good. So we're sort of, the industry is sort of on the cusp of a transition between two different paradigms, I think. Historically, like Alejandro was saying, buildings were drawn on 2D, right? And then somehow they became physical 3D objects. And right now, given where we are with technology and speed of projects and what we're capable of doing virtually, we are transitioning from 2D to 3D to a 3D right away virtual representation of the project to a physical representation of the project. And this is sort of like underneath the hood, what we're doing these days to try to get there. So historically, on the top left-hand side of the slide there's a design team saying we've put together a design model that's at a certain level of development, not ready for fabrication, but good enough to do drawings, that we spent maybe years or months making. But it's just for reference, right? Somebody else needs to go and create the fabrication model, create the fabrication drawings. But you can use our stuff that we designed for reference. Contractor says, great, thanks. I'm going to go out and get my team to put together a fabrication set of drawings, a fabrication model from all that design reference information. But all these guys over here working on the build side, they've got questions. There's missing detail, or there's unconfirmed details that have to eventually get figured out to get the building built. So they're going to send through RFIs, requests for information, back to the designers. And now they've got a fabrication-ready model that can go into production for structural steel or reinforced concrete or what have you. And then they send it back to the design team to ask, hey, does this meet your design? If it doesn't, or if it does. Okay, so this process is obviously cumbersome, and it's being compressed in today's environment by desires to go faster and increase design ambitions. There's time, money, loss of knowledge, loss of time, loss of money through this entire cycle. And so there's benefits to early coordination on the virtual side of the project. If you can get the entire building figured out all the way to fabrication level, you can solve a lot of these headaches. And that's where we are. Certainly this is the process that we followed on the USF Honors College project, where we reformatted project delivery working with the BEC team to say, okay, instead of this huge do loop, right, complex project that we want to achieve a certain schedule on, let's go directly to fabrication level modeling, all on one side of the equation. Eliminate the RFI do loops and confusion about design intent. Make sure everybody on the build side has a better understanding of what needs to get into the physical environment right away. So there are some benefits to the early coordination here. Back to you, Alejandro? Okay.
Go back to the coordination part. Thank you. Are we good on the mic? I think we should be good, right? Yep. So Stephen talked about the differences and the advantages of having an early design and involving a lot of the team members. Construction coordination is a little bit different. So what are the differences for those of you that study architecture, engineering? What are the differences between design coordination and construction coordination? Anybody? Nope. What do you think? No, anybody? I think you want to participate, right? No? Okay, I got it. Well, the differences are in design coordination, we have the engineers and the architects doing that coordination. The construction is where you have your plumber, where you have all your teams that are the trade specialties doing that coordination. And you might have some of the architects and some of the engineers in those coordination sessions, right? This is the MEP coordination process long time ago, before you were born probably. We had the The light tables, we would put paper on top of a light table, on top of, or a piece of paper on top of another piece of paper. We would overlay those, and we would see how the installation overhead was going to work. But it was a process, a cumbersome process, and it was a 2D process, so we had a lot of issues with that. We also had overhead projectors. Any of you worked with overhead projectors? Nope. You have. How come? You look very young.
Elementary school.
Elementary school. Okay, so in elementary school you did get some of these. Okay, but not anymore, right? You don't see them at USF. You don't see them anywhere. Perfect. Those pieces of plastic, paper on top, right? And we would overlay, and we would see that the installations would work. So this was a process, right? We would draw, we would coordinate, we would produce information that then the teams could use for fabrication, and then the teams would fabricate. Pretty much, that was it. It was an easy process. The difference between BIM, you can see the only difference that I've identified here is now you have an information model. So forget about BIM, remember information. The important part of BIM is information. Some of you are studying IT, right? You're going for technology, information major. So the information part of an building information model is the most important part of it. So we have an information model. It's a 3D geometry, as we mentioned. It has 2D drawings, and we could put a lot of other information in there. That's the difference between the previous process, which was only 2D drawings, not a lot of information. So you had one job, right? We've seen this happen sometimes in our houses and the places where we work at. BIM coordination tries to improve that by the most known clash and interference, clash detection, interference detection. Also, clash avoidance. We are trying to avoid issues, not only find them, but let's avoid them. And then design review. We could also work with the architect and the engineer and check that the design has been reviewed, and we can look at the model, and we can, for example, we were talking about you guys are looking for an apartment. Do you want to have 2 rooms? Do you want to have 3 rooms? Do you want to have 1 restroom or 3 restrooms? That would be part of the design review. You would have a model. You could talk to the engineer and the architect about that. Constructability, we'll talk about that one with the model here in a minute. And then operations. So look around you. Everybody, please look up. What do you see here? You see some lights. They're the light fixtures on the same location up here. What about over here? Does this look correct? We got some air diffusers here. These don't look aligned, right? That could be part of the design review, but also constructability. Do we also want to do that? Was this an issue by the architect, by the engineer, or by the construction teams, right? Why don't they look aligned? You can see that right away, right? So the model helps for operations also when you need, for example, at your home, you're opening up the fridge. You need a certain clearance so you can open up your fridge, right? So you can access your fridge. For equipment, you need a clearance and you need an operations. You need to think with the end in mind and with the future of that operation. A lot of engineers will have issues just like this one, but you got to trust them, right? Trust me, I'm an engineer. So for those of you that haven't studied or haven't taken any classes of engineering and architecture, just a quick update. That one on the top left-hand side, that's a duct, right? HVAC, heating, ventilation duct. We have cable tray in the middle. You've probably seen this one down here. That's a flexible duct. That's a light fixture over there. And this right here is what we mentioned about the clearance, right? If you have an electrical panel, you need some clearance around it. So it's an imaginary space that you need for people to do maintenance to it. So I'm going to open up the model so we could start looking at it. And for those of you online, please give me a minute so I can share my screen. All right. Grant, can you see the model? Give me a thumbs up, please. Great. We can't see it on the big screen, right? Grant can see it. That's a little better. All right, so let's look at the model. This is the USF Honors College model. I brought a joystick with me today. Who wants to try out the joystick and look at the model? Come on. You play video games? Some. All right, so just like a joystick, you can play around. You want to try it? Give it a try. All right. I'll show you here in a quick second. Let's look at a few views before we go to that. So these are examples of clash detections. Oh, that one doesn't look quite right. It actually does a little. So what you see there in the pink, that is a duct like we saw earlier in that picture. The duct is clashing with a cable tray. That's an example of a clash. We have another example here, 3D view there, isometric view. So these are examples. What was that? The brown is a cable tray, pink is a duct, the red is the fire main. So we have a few clashes there, right? We don't have enough space. So what we're using the model for in this instance is to understand geometry versus geometry. Can that fit? We have a concrete beam here. Can that fit here? Can our flex duct go underneath this concrete beam? We start looking at the model and identify any constructability issues, any clashes, any design issues. Here's another one, the same flex duct clashing with the concrete beam. And then light fixtures, we also saw an image of a light fixture earlier. That one is clashing there with a duct. You can see that duct orange up on the top. So we could talk to the architect and the engineer and let them know about that issue. And they could provide us information if they want to lower, if they want to make the duct smaller, or what they want to do in the design, right? That's another example there of the same issue. So we were talking about aesthetics, and we looked at the diffusers here, and we looked at the light fixtures in this room. So we also wanted to check with the architect if they're good with that design. A constructability issue here that we found in the model was we had these two pipes. We're looking down a floor plan. We have these two pipes in there in the middle of the wall, and those pipes are they're pretty big for that wall, so we want to let the architect know, and if we can make that wall thicker, that could be a constructability issue. And we talked about the clearance issue, operations. So we have a panel here to your right. What you see here in transparent green, that's the clearance. People will not be able to access and put their hands in there and work through here or work on the panel because there's some pipe right in front of it. So that's something that we also identify with the model. And this is another view of that. Let's play this animation just really quick. You're going to have to forgive me. There's a few. Oh, I can't see it. Is there a play button there? There we go. All right, I'll take that back just for a second and I'll show you how to do it. So turn it off. That's going down, up, turning to the sides, front, back, left, right. And just give me a minute. So this is the model, construction model of the concrete, and we have the give me a quick second. Yeah, it moved away. Can we turn that one off for a second? Yeah. Yeah, yeah. All right. Let's go back to that one. Yeah. Technology is great, but we also have sometimes a lot of issues with it, right? It's getting there, though. Okay, so I'm gonna have to move it away. Thank you. I'll just do it from here. Why don't I just sit down and do it from here? Can I do that? All right. Let's stop this animation. It's upside down now. I'll have to do it from here. So sorry, guys. We're back on that one. I'll just do it from here. So that's our model. It has, right now, it's only showing the concrete. You could see all the levels there. If we have a point cloud, which is a scan of the conditions in the field, we could show it also. Right now, this model shows the overlay of concrete and the MEP services. So all the duct that we're looking at, all the pipe, right? We start putting a lot of information to our model from all disciplines. This one now shows the point clouds. So that's a scan, and Grant will talk about the point clouds here in a minute. That's a scan of the existing conditions at some point of the building. All those lines there are reinforcement bars. So if any of you have worked or have walked next to a construction site, you've seen those rebar, right? Reinforcement bars. So those are millions of points in the scan that show us the existing conditions. So Grant will talk about that in just a second. Grant, I'm going to hand it off to you here. Give me a quick second.
And you tweak it and you change it and you coordinate it, but it's still that base information that needs to be as accurate as possible, right? It's changed the way that we approach the life cycle of any project at all. There's so much more planning, so much more upfront effort that goes into making these projects successful. And the more constraints that we get put on the process in its entirety via cost constraints, schedule constraints, et cetera, it compounds even more the importance of this information, because we've all heard the phrase garbage in, garbage out. This takes it to the next level. So if there's garbage in up front, you're destined for exactly right. Sorry.
Yeah, that's exactly right. It's easier
Okay. All right, cool. So Chris was talking earlier about how the model that we're developing prior to the project going physical, so to speak, is becoming more and more important. And its value is a function of how much information you can get into the model, how much quality information you can get into the model. So in this segment here, we'll talk a little bit about, on the design side, starting that process, right, before you get building trades involved and getting the model to a fabrication level. We'll talk early in the process here for a few slides. All right, my poll question is, what's the most important step in the waterfall of systems delivery? So we'll talk about that here in the next few slides, but you can put your answer in here into the poll. I guess Steve has running. Whoops. You want to put it back in presentation? We have nav is up. There we go. Okay.
Most people are saying the design phase.
Okay, very good. For this, what's the most important step? The truth is they're all important. They're all critical. They all add a certain amount of essential information to the virtual model before the project goes physical. And just very roughly, this is when I say waterfall of structural systems delivery, this is sort of what we have in mind. This is the traditional way of thinking about a project. You start all the way over on the left with kind of massing and general geometry. Then you work through your analysis programs, your construction documents detailing, all the way to the project going physical, erecting it, and going through your punch list. Well, this process is getting squeezed, it's getting accelerated, and you have multiple systems, multiple teams working on the same information in sort of an iterative do loop. And again, it's cheaper and easier to do that in the model before the project goes physical. Once it goes physical, you only get one shot at getting it right. And here's a visualization tool for these projects. You know, I was talking about information going into the model being critical, and really over the course of time is the left axis here. The project is an accumulation of information, either instantiated virtually or instantiated physically. And so taking care to keep that integrity of the information is super, super important. On the design side, this is a little bit about what our process looks like. Left to right, sort of moving down the waterfall. This is a project we did a few years ago, but just having systems in place on the design side to be able to move information around to the different platforms that you need to be using to deliver the project is super important. So analysis models, this is SAP, that's what we use frequently for structural analysis. You heard the term Revit earlier. Tekla is another software platform that's used in our industry for fabrication modeling. How do you do this? You're not going to be doing it manually. You need to build systems to move information around where you need it. And so on our side, on the design side, we've built some proprietary methods for making that happen. And just, you can sort of walk through what we were observing years ago, trying to use a bunch of different software platforms. Revit on the left is what we use for coordinating with architects. Tekla on the right is what we use to create fabrication level information. So you got to move a beam from Revit to Tekla. How do you do that? You know, do you manually redraw it, or do you try to push it through intelligently with some custom automated tools? We've taken the latter approach. If you try to do it manually with multiple software programs, as you keep adding them to your process, analysis programs like SAP 2000, ETABS is another one that we use to design columns and beams. You have this like geometric increase problem. And you do that more and more, and pretty soon you're just managing information flow and not designing anything, right? So on our side at Walter P. Moore, we've developed this central interoperability database to keep data as data. And our columns are not virtual elements, they're pieces of data, right? That we can move to different spots in the delivery process as necessary. And this is what allows us to iterate and coordinate with other members of the design team. Okay. Kind of summing up, this is our general process that we've built, and we've taken on a sort of I would say a 5 to 10 year journey to get to the point where we've got this SID built and we can move information around like I was talking about earlier. Tekla, I mentioned, is the tool that we use for fabrication level modeling. Once a project gets to that point, that's where it's able to go physical. And what I mean by that is from the fabrication level model that we've developed in Tekla, we can export CNC files. That stands for computer numerical control. These CNC files are literally instructions to machines on the fabrication shop floor on how long to make this beam, where to drill holes, and that sort of thing. And so all of that is automated at the structural steel fabrication level or the reinforcing steel fabrication level. Then those submittal drawings that I was talking about earlier, those get exported from the fabrication model as well. And if we've done this intelligently, that's just sort of a check the box step rather than, design on shop drawings step. Field use drawings are created from that model, and that's what goes out to steel iron workers, rod busters. Typically, the field use drawings is what you're going to see out on the job site if you're walking around and making these tours. And then it can be used for field validation. Alejandro was with fabrication level models that we had exported from Tekla for the reinforcing steel. Okay, this is back to Grant, I think, right? Okay.
All righty. Can you guys hear me?
We can hear you, Grant.
Perfect. Well, let's launch the next poll question here and kind of transition things towards getting out in the field. So a kind of fun poll question here. What are lasers used for in construction? We got a couple different options here. Cutting, measuring, marking, all of the above. I feel like we're going a little futuristic here on the use of lasers, but what would be y'all's guess on what they may or may not be used for? Seeing a pretty heavy response in the all of the above, which would be correct. And so we're going to dive into one of those here in that kind of realm of laser scanning. So we talked a little bit about this at the beginning, and a lot of what we've kind of discussed and been focusing on has been the virtual world, right? So we're talking about models, we're talking about coordination, we're talking about how all these systems get built virtually before we actually build it physically in the real world. But a big gap that our industry has is what are we doing to validate what's being installed out in the field actually matches the amount of effort that was put in to build it virtually. And so this process, or this virtual design or construction process of laser scanning, is one of those methods that we're going to kind of talk a little bit about of how we're using that out at USF in kind of a little bit more specificity. So if you click on, I think this is a video, Alejandro, if you click on it, it will kind of describe what laser scanning is, and I'll kind of talk over it a little bit as this is going. But this surveying equipment emits a laser that you can't see, but it's denoted in green here. And what's happening is it's rotating around and it's hitting objects that it sees in its path, right? So as this thing is spinning around, it's collecting all this data and information from that position, and it's locating its position back to the scanner itself. And so it is, it knows its coordinate based on the distance and angle of what it spins from the scanner. So think of this as like a laser tape measure on steroids, essentially, that's spinning around and collecting all this different pieces of information. And what you're seeing here is a point cloud. So Alejandro talked a little bit about that earlier, but a point cloud is a physical representation of the space that is captured. And so in this case, this was a oil refinery plant that it captured that existing conditions. And so this is a method that we use to validate what is being done in the real world is matching up to what time and energy and effort was spent in the model world to make sure is correct. So we have the real world living out here, the model world living over here. How do we bring those two pieces of information together to make sure that what we are doing is correct and valid? So there's a lot of different parts and pieces to this, but the best part is that it has gotten very, very easy to use and streamlined for even someone like me that I have very little experience in this. But if you give me an iPad and something and a couple of YouTube videos, we could go and teach you very quickly what this process is like. But in the laser scanning world, these red dots that you see are called setups. And so you would take your scanner, you would set it up, you would capture its conditions, it would rotate around like you saw in that video, and then you'd move it to another location, and we combine these scans together. So really what we're doing is step one is scanning in the field, step two is combining all those scans together, and then step three is to bring that into the model world of what Alejandro was showing to validate what the real world looks like versus the model world. So that's kind of the three-step process that we've been doing out at USF on the Honors College to validate and make sure that what we're putting in is correct versus what we've spent so much time coordinating in the model world. So some of those examples of when things don't go right would be what you're seeing here. And so what you're looking at is examples of embeds or things that go in the concrete floor to make sure that different steel elements that get attached to it are in the right spot. In this case, obviously it's not. The slab penetrations or sleeves that you see here, obviously those are going to show up and validate and show us, hey, were those put in the right spot or were they not? And really what that process looks like is we're setting up these targets to make sure that we use that for alignment of the real world versus the model world. We're setting up those scan locations all around the slab of what you're seeing here before it gets poured as kind of our final check to say, hey, we got all these elements in this slab, whether it's a mechanical, electrical, plumbing, embeds, and we want to make sure that they're in the right spot. So these little blue orbs are similar to those red dots. We set up those scan locations around this area that we're going to pour concrete in. That's like finalized, done. And so before we do that, we'll do this process. And the next step to that is then combining all those together and linking them, which you can see in those lines that are connecting those blue dots. The purple boxes are what we call the site control. And so there needs to be some sort of piece of information that ties this real world to the model world, which is what you're seeing here in kind of a top-down view. And so once we have that all combined together, then that's when we start to bring that into the model world and what you saw from what Alejandro was showing earlier. So again, this is kind of the closing of the loop process to say, okay, we spent all the time in the coordination world, making sure these models are correct, everything looks good, but now we need to bring in the real world as a part of that component to make sure what's actually going on out in the field is visually correct with what we spent all this time in the model. So these are some examples of where things don't go right, and we get to catch that and make sure that they get corrected before we, again, pour this concrete that's like set in stone. It's forever in place, or we'd have to go and make some adjustments that would take a lot of time and cost and money. So again, we talked about the BIM world, which is the model component, and the VDC side of it is what we kind of just walked you through with what reality capture or laser scanning looked like. I think Alejandro is going to take it from here, kind of land the plane, and talk about really where we see the future of this stuff going with some other applications.
Right. To close out, what are the synergies with other industries? What are the future applications? What about how do these technologies apply to what each of you do in this room and everybody listening to us online? So what is the future of design and construction? We've all seen 3D printers nowadays. They're very common. They're cheap. We are using 3D printers in construction, right? We have automated procedures to have a 3D printer out in a construction job site, print in concrete and steel. We also apply that to printing organs. What Grant mentioned earlier, the digital twin. Digital twin is having a digital version of any object that you can imagine, right? So you can have a digital twin of your house, and you have information of your house, and you have all the data you need in order to track the consumption of energy. You can track and connect other devices to it. You can use it maybe in your future Ethereum games. We talked about BIM a lot today, but we also have CIM, so Civil Information Modeling. As mentioned before, we have information model, but we want to use it for buildings, that's BIM. If we want to use it for the civil industry, it's CIM. And that encompasses roadways, bridges, and any underground utilities that are part of a civil scope. Some of you have heard about GIS, Geographic Information Systems. That's been around for a long time. Now we're using it in Google Maps. We're using it in a lot of the tools that we use to get from point A to point B. In the future with smart cities, we're going to start using this a lot more and tying it to the BIM models, the CIM models, and bringing it all together. So now we have a smart city. We have a database of a lot of information of a city, including buildings, including everything around us. Some of you have already played probably VR or AR games, right? We also use those for our industry to design out in the field to verify that the conditions that we have in the model are actually being installed in the field. And those technologies are also being used at the moment with healthcare, right? And they could be used for a lot of other things. One of them being the user-centered design. So right now we're designing buildings with what the owner provides us, the input that they provide us, what they want to see in their building. But what do you think about having the doctor from a hospital coming into our design team's office and putting on a virtual reality headset and telling me, no, I don't want the beds there. I want them on this side because I'm left-handed or I'm right-handed. This is going to be my room. This is where I'm going to be working every day. So this is how I want my design. It's going to be more user-centered design, but we're going to be using those technologies. So with this, I'd like to finish and pass it on to.
All right. So to kind of drive it home, so a lot of this is geared about efficiency and accuracy, economy, because everything, the mighty dollar drives everything. But ultimately, it's about simplifying the process. I mean, way back when I was, so when I started my own architectural firm, I used to laugh because my wife kicked me out of the house and made me get an office for my firm because I turned our glass top coffee table into a light table so I could overlay certain drawings and do that coordination like you saw back on the screen. Now they're doing all that electronically, and what is really cool is not only are they doing the coordination electronically, but they're the fabrication, as you heard Steve talk about. So back in the day, so we would get the design drawings, we would get the shop drawings. It was always the young architects, the intern architects that had the job of checking the shop drawings. So you'd look at one set of drawings to make sure that the beam was the right length and the right height and actually fit and connected with the other beam and everything like that. Right now, Walter P. Moore is actually doing that in their shop. And then instead of sending the shop drawings, they're actually sending those to the rebar company. And the rebar company is putting it in their machine, and it's actually bending the rebars, selecting the right size, bending it the right length, the right angle, and everything like that. They're doing the same thing with the steel beams. So that is probably cuts about a month and a half just in that process alone, easily. I'm seeing Dylan back in the back shaking his yes, but it is. It's a lot of time saving, and sometimes it creates that higher level of accuracy. There was an instance in Kansas City back in the 80s when I was going to school, and it was actually a problem when somebody was checking the shop drawings, didn't catch something, ended up being a problem with it, and was it kind of like a sky bridge fell, killed about 160 people in Kansas City. Was really nasty, but it boiled down to the person who was checking the shop drawings didn't click and said okay to something that really wasn't structurally sound. So this process is really changing the industry considerably. For those of you in computers, what did you guys think? Good? You like it? So the other thing is, so the point cloud scanning, that was kind of cool. Okay, so they got some sleeves a little bit off, but really where the advantage to that is going to be, and you're going to see that probably next semester as you start seeing the building going up, is they're taking that point cloud and actually sending it up to New York where they're building the actual skin in big giant panels, so they can make sure that the connection points for the giant panels on the skin are actually connecting in the right place. And if they've got, you guys saw what an embed was embedded in the concrete. If an embed's just a little few inches off, they can correct it up in New York before they ship the product down. The same thing with we have what I think Beck is now affectionately calling the French fries in the, not publicly. Okay, well, I just let the cat out of the bag. But so the matrix in the atrium, that's being fabricated in Dallas, Texas. So the connection points for that, if they're a little bit off, they can adjust it now while they're doing the fabrication in Texas before they ship it out. Because 10 years ago, it was like the architect be sitting in his office and saying, okay, this is off 4 inches. What do we want me to do? And I've got 10 guys standing around waiting for an answer. So it avoids that problem a whole bunch. Okay, so what is somebody saying on the chat? What are they saying? And thank you for joining the chat online there. So Grant Ballard raised your hand. Can you, unmute your mic and maybe say something?
Yeah, I was just wondering how often throughout the construction phase of the project those full point clouds get generated.
I'm going to unmute here if you want to mute.
Okay. I can mute it this way. Thank you.
Grant, we can hear you now if you want to ask your question.
Yeah, I was wondering how often during the construction phase of the project do those full point clouds get generated?
Mr. Grant, you want to take on that one?
Yeah, that's a great question. I think it just depends on what the project sees as needed to validate. So for us, a big part was validating a lot of the elements that were going in the concrete slab. Some slabs, and this one in particular has what they call post-tension, which post-tension just means that we stress the concrete slab after we pour it to make it a little bit stronger. And to go back and, I guess, drill into that slab after you tension it just leads to a lot of issues. And so in our case, we really wanted to make sure that everything that got put in the slab was 100% correct before we poured it. And so that's why we said, hey, I think it's the best for us to scan before we have any concrete that's poured to make sure that something gets caught if need be. And so I would say that's not very common, but could be done. I mean, obviously we're doing it in this case, but a majority of it, I would say, are for just key milestone activities before you cover up anything that would not be able to be seen after the next scope of work comes into play.
Yep. So as with everything else in design and construction, there is no one right answer. There's no set process that shouldn't be modified for anything you design or build. For the Honors College, we have very specific reasons for scanning. What Steve was mentioning earlier with the exterior scan, 75% of it is a prefabricated system, which means it needs to be, the level of accuracy for the embeds is critical. Same thing for the interior architectural feature. We scan for those very specific reasons on top of scanning for each concrete pour. In this case, each deck is broken out into 2 pours. So the usage of all of this technology is very much dependent on what you want to get out of it and what the project conditions are. So it's the best thing we could tell anybody going in, you know, coming out of this presentation or going into this industry in general is don't look for one right answer. Take the tools, take the availability of these resources, and implement them as you see fit and for what fits the purpose of what you're trying to achieve.
Well, and piggybacking off that too, so from the owner's standpoint, it becomes very valuable 10 years after the building is built, and we've got to make a modification to the building. Now we know what's actually in that concrete slab instead of having to do a radar scan or x-ray scan and figure out what's actually there. Before the drywall goes on, we've got pictures that actually says, okay, there's a big water pipe right there. So don't drill a hole through that piece of drywall. Had that happened on the Sundome, had they looked at the information, they would have said, nope, don't drill that hole. Kind of created a big mess, but it's having that information available to the people that are maintaining the building. As you saw the big figure 8, you know, we start with the design process, and I see you all looking at your watch. We'll wrap it up here in about 30 seconds, but in every building has that life cycle, and it comes to that age where we start needing a facelift to certain buildings. Hopefully we're not tearing them down, but we're facelifting them and renovating them. So it really helps to know what's there, what's the bones, and what can be taken out, what can be modified, and what do we have to maintain. Any other questions? No questions? You ready to get out of here? All right. Thank you very much. Thank you, Grant, for asking the question. Thank you.